got full of themselves. They thought that their diversity across the world was going to save them. It didn't, because there was a contagion factor where if something goes wrong, or something went wrong in Japan, that spread over to China, that spread to Russia, that spread to Europe, that spread to the US. The result was a huge multi-billion-dollar bailout. So you have to consider these factors in your models. When is a $6 billion more important than $30 billion? When your company goes into receivership because it can't come up with the $6 billion in 7 days. And that happened to a company that I worked for, General American Life. They had a provision in the contract that said you had 7 days to get your money back. It was basically a gift that was bought by pension managers, and they are bound by very strict rules as to what assets they can hold. When the Moody rating of the company went down by 1 point, it became a threshold. There was a run on the bank. The $30 billion company went into receivership. How many companies do you know that could come up with 20% of their assets, even Apple or Microsoft, in 7 days? None of them, really. So you have to consider the other factors besides your numbers when you're going into your model. All right, what if all your pictures could be scanned for the use of tobacco? Your cable company revealed whether you have the premium couch potato package, your wrist monitor was streaming vitals by the minute wirelessly, and your fridge was reporting on your food purchases, and your shoes relayed how much you walk, and your clothes were all gathering info and sending it along. What if the prescription pill you take has an embedded nanochip that travels through your bloodstream and sends signals to your smartphone? Oh, it goes on and on and on. But this is what's happening. It's a new world there. We have to get ready to embrace that. Euclidean distance examples. That's simple in 2 dimensions. We all know that a squared plus b squared equals c squared, and that's really cool. But the cool thing is that it works in higher dimensions too. So we can go ahead and figure this out. And once we do that, we can apply this to higher dimensions. But there's a danger when you do that. When you're applying stuff to higher dimensions, you have to realize you're only looking at one perspective on there. If we look at Orion up in the sky, it looks like Mesa is very close to Bellatrix. Actually, we are 4 times closer to Bellatrix than Mesa is, because we can't look from the side there. We can't see that other dimension. And when you take your data clumps and you show them in 2 dimensions, or even 3 dimensions sometimes, what you're seeing is often a very misleading picture of what the data actually looks like. It's very difficult for us to accurately comprehend data beyond 2 or 3 dimensions. It may look like it's okay on a 3-dimensional plot, but it's not when you actually see it from other perspectives on there. So be very careful about that. Michael Murphy has some great links out there for anamorphisms, where you see some impossible looking sculptures. All right, Euclidean distance. I said it can be extended to any number of dimensions. Here's a simple 11-dimensional variable situation. You have 2 points in 11 dimensions, and the distance from point 1 to point 2 is going to be the square root of 1 minus 0 squared, 3 minus 3 squared, 0 minus 5 squared, 2 minus 0 squared, on like that there. So we can actually come up with a number. We can come up with a distance number. When you're doing the clustering, the number can't be negative. It has to be 0 if you're going from a point to itself, and it has to be symmetric. If you're going from A to B, the distance is the same as from B to A. But given these rules, you can choose any number of different metrics for distance, and there are lots of different metrics that you can choose for distance. Euclidean's the most common, but it's not always the most appropriate. Why would you normalize your data? Our sense of normalization is to keep one parameter from overwhelming all the others. Typical example from Amazon is the square footage of a house. You don't want that to be treated exactly the same as the number of bathrooms. Maybe bathrooms are important to people. They are to me, I know. But square footage would overwhelm those if you don't normalize the data first. Okay, why do we care about data classification? It gives us some appropriate ways to normalize that data there. Zip code might be nominal, as suggested in most texts. It might be ordinal if it's transformed to relative cost locations. You know, zip code 62002 in Alton, where the median price is about $80K, is going to be a lot less expensive than the zip code 90210 in Beverly Hills. Quantitative observations. Box and whisker plots and violin plots are often helpful in the analysis of raw data and the choice of how to normalize it. alternatives. Things like spectral clustering and others might be more appropriate depending on your data distribution. There are lots of alternatives to k-means. A Gaussian mixture might be a better fit for some situations. Here's a website that you can go to that shows you lots of different distributions and what would happen under the different clustering techniques there, how well that would fit the various distributions. I like hierarchical clustering a lot. I really like that, but one reason is it's easier for non-mathematicians to visualize. And you can take a whole lot of dimensions there and get not only which ones are closest to each other as far as clustering, but get an idea of how far apart they are too. And that becomes very important. I've written an article on hierarchical clustering, and you can see that there too. I'll give you 4 quick slides on how to do hierarchical clustering in R, and you can go through those after. Now let's jump to neural networks. Neural networks, artificial neural networks are really, really cool. That's because real neural networks are really, really cool. Real neural networks, the one that I'm holding there is an actual human brain. It's been colorized. That flap that you see on there is the meninges. If that's infected, you can get meningitis, but we all have about 86 billion neurons, maybe some people less than others. You probably know some of those people, but they have tons of connections involved. Here's a very oversimplified picture of a neuron, grossly oversimplified. Typically, you'd have around 10,000 different dendrites or inputs coming into that soma there. The axon could be as short as a couple millimeters if you're going from one neuron in the brain to another, or it could be as long as a few feet if you're going from the base of your spine to your big toe there. At the end of that, you have these terminal buttons that allow you to have jumps or synapses, the gaps to other neurons, dendrites there. And we have hundreds of trillions of these things, and there's all kinds of feedback loops. And it's not just electrical, it's also chemical for the calcium and phosphorus and other ions in the mix. What's an artificial neural network in the context of machine learning? It's just a metaphor. We use the biological neuron as a metaphor for the artificial neural network. It's so much simpler by all measures. Okay, all we have is we have a bunch of input. Our weights are going to be the counterpart of the synapses there. That's what you have to go through to get to the soma. And once you do that, once you've done your summation there, then you want to use some sort of activation function to transform that. You could think of it something like normalization there. So you transform that, and then you have your output coming from that. Activation functions could take many forms. They used to start out in the old days as a threshold function. That was not very flexible and didn't have a derivative at important points here. So the sigmoid was chosen because it had 0 to 1 as a nice range that it would compress everything to, and it was differentiable. If you wanted -1 to +1, you'd use hyperbolic constant. But those have been pretty much cast aside in the deep neural networks now by the ReLU, the rectifier function, or the leaky ReLU for the GANs. Okay, Perceptron. It was the beginning of this whole thing, but it couldn't do anything like an XOR function, which is very simple because it didn't have any hidden layers. Once you add the hidden layers, you add a lot of power to your artificial neural network. Again, it's a simple concept. You have your inputs, your hidden layers, and your output. How does this work? Well, you start out with your weights or your synapses. You randomly initialize those to small numbers, but not to 0. Forward propagate that vector of the first observation. You get your predicted results there, the y hat. Each feature goes into one node of the input layer. You compare your y hat to the actual values that you want, and you get a cost function. Once you have that cost function, you say, okay, how can I reduce that cost function? What part of the cost function was attributable to this weight over here? What to this one? Unlike that, and you work backwards there. That's called back propagation. Okay, when you're doing this, gradient descent is a nice method, but often gets you in a local minimum. So stochastic gradient descent is often used to test several bands at once within the range, and that will often get you to a global